right, guys, we're looking at lesson 13.2, task 3. All right, it says growth of linear and exponential functions. Complete the proof that exponential functions change by equal factors over equal intervals. All right, they're giving us a statement again, and they're wanting us to use it to prove something else from that given information. So it says given x2 minus x1 equals x4 minus x3. If you remember in the last task, we did this with a linear function. Now it says g is an exponential function of the form g of x equals ab raised to the x power. Okay? All right, so again, I'm going to blow this up a little. All right, so it says the proof. So it says g of x2 divided by g of x1 equals g of x4 over g of x3. So this is what we're trying to get. This is trying to prove this given this information here. All right, so start with the given information, and they're going to use properties of exponents. If you remember, two exponents have the same base, then x can equal y. So b to the x equals b to the y, if and only if x equals y, okay? So that's our properties of exponents. So what they did was take what was given, and they took both sides of the equation and put b to that power, all right? So again, just manipulating equations for the sake of proving this information here. All right, so remember with properties of exponents, when you subtract, that came from division. Okay, so b to the x subscript 2 over b to the x subscript 1. Because they're dividing, that's where same base, when you divide, you subtract your exponents. So number 3 would be the quotient. Quotient is division. That would be the quotient property. All right, and then from here, they're going to multiply each part by the same thing, a. Okay, so they're just multiplying everything by a. If we do the same thing on both sides of the equation, we're not changing the equation. But step 4 would be the product, nope, that would be the multiplication property. All right, because we simply multiplied by a. Okay, all right, now ab to the x power, that's just your definition of your function. So g of x equals ab to the x power, and the subscript is just indicating which x value it is. So when we get to step 5, g of x over 2, okay, that's ab to the x, and that's just the x2. And right here we've got ab to the x, and this is my x subscript 1, that's g of x1, and so on and so forth. So that's just definition of g of x. Again, g of x is like y equals, and this is basically saying, given the x values that we started with, we can rewrite it as y over y equals y over y. All right, so that is all for task 3. If you have any questions, please let me know. Lesson 13.2, task 4. All right, so compare linear and exponential functions. In real-world situations, when a quantity increases or decreases by a fixed amount, a linear function is the best model. When a quantity increases or decreases by a fixed percent, an exponential function is the best model. Brooke and Phoebe have both made an investment of $1,000. Brooke invested in a bond and Phoebe invested in a certificate of deposit, or a CD. The tables show the values of their investments each year. Write functions that model the values of each investment and graph the models. All right, so you can see in the first table, Brooke's investment. So it goes time in years, and it goes from 0 to 5 years, and this is the value of her money. So the difference is $40, so there's the same difference each time. So from 1,000 to 1040, 40 to 80, 80 to 20, and so on. There is a difference of $40 in each investment. Okay, so the ratio from 1 year to the X, if you go from this to this and divide, it changes a little bit each year. All right, so Phoebe goes from 0 to 5 years. She starts with initial investment of $1,000 and it goes up by $37.50 and then $38.91, and it changes. You can see the difference changes each year, but the common ratio stays the same. All right, so when the common difference is the same, this is going to represent a linear. And when the common ratio is the same, this is going to represent an exponential function. All right, so that's our two tables. And it says determine whether differences or ratios are constant. For Brooks' investment, the difference are always 40. A linear function is the best type of model for the value of her investment over time. For Phoebe's investment, the ratios are always 1.0375. An exponential function is the best type of model for value of her investment over time. So for Brooks' model, to write an equation for it, we're going to have V equals mt plus b. So that's just a version of y equals mx plus b, where t is time, and then v was the value. Okay? And then m is always your slope, and b is your y-intercept or your initial amount. So it says, in Brooks' investment, what is the real-world meaning of the value of m and b? Match each variable to a description. All right, so m, that's your slope. That means it increases by $40 annually or each year. And b is your y-intercept or your initial amount. So you start with $1,000 investment. All right, Phoebe invests. V equals AB to the t power. This is your exponential function. Okay, it's the same as y equals A times B to the x power. We're just using t for time and v for the value. Okay, so just changing up the variables a little bit doesn't change the equation. All right, so A is your initial amount, 1,000, and then 1.0375. So that was that's the rate of increase. So you can see that's the ratio given here. When the difference is not the same, it has a common ratio. All right, so this would be 1 plus your interest rate. So it says, in Phoebe's investment, what is the real-world meaning of the value of A and B? Choose the word or phrases to complete the statements. So the value of A indicates the initial amount, and the value B indicates the growth factor. And it's growth because it's greater than 1. Remember, if it's between 0 and 1, it's decay. All right, so if we graph the two models, this is what it's going to look like. So we have T, our time in years, across the bottom, and we have our investment amount going on the y-axis, or in this case, the v-axis. So they both have an initial value of 1,000, and you can see that the red line is the linear equation. It's going to be a straight line, and you can see the blue is exponential, and you can see after so long these two lines spread, and the blue line begins to get steeper, and it's going to start rising more quickly. All right, so let's see what the next question says. It says, on the interval 0 to 5, so from 0 to 5 years, the models have approximately equal average rate of change. So that's true. How do the graphs of the models compare? Select the word or phrases to complete each sentence. The models have the same initial investment. The model of blank investment is exponential. So that would be the blue line, or Phoebe's, and grows at a faster rate. All right, so the blue line, you can see that came from the exponential function, a times b to the t power, and your growth rate here is about 3.75%. All right, how can you use the average rate of change to conclude that after t equals 5, the value of Phoebe's investment grows faster than Brooks? So the average rate of change after 5 years is, all right, so if we go back up to the top and we're going to look, and it says, All right, so the average rate of change after 5 years per year for Brooks investment. So Brooks investment was the first table. So we're going to have 1,200 minus 1,000 over 5 minus 0. So that comes straight from our table. All right. And then it says, and blank dollars per year for Phoebe's investment. All right. So Phoebe's investment, let's see. So it can't be 5 minus 1. It's got to be 5 minus 0. What was from the table? So it's going to be 1,202 minus 1,000 and 5 minus 0 again. So 1,202 and then it says the latter is greater than the former. So after 5 years, the value of Phoebe's investment grows faster. You can see that 40.42 is faster than 40 than Brooks. All right, that's all for task 4. If you have any questions, please let me know. Lesson 13.2, task 5. Linear and exponential functions and their graphs can model real-world situations. Often models do not fit the data exactly, so differences or ratios between successive intervals may not all be equal. A sea turtle population is studied in a coastal area. The data show sea turtle population estimates during a 5-year period. Find a model for the data and analyze its fit using a residual plot. All right, so it says population over time and change in intervals. So you've got time from 0 to 5 years, and we've got the population of sea turtles go from 19,000 down to 12,500. So this is their difference. So we've got negative, 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 but these are all changing. And then we've got a ratio, 0.92, 0.89, 91, 94, 95. So these are all different, but they're kind of similar. Okay, they're kind of close. Closer than the difference, that is. Why does the exponential model fit the data? Select the correct word or phrase to complete each sentence. All right, so exponential. All right, you're talking about ratios. Remember, the common difference is linear. So your ratios between the successive y values per unit of x values are roughly equal. Okay, so they're not the same, but they're close. Roughly equal just means these are kind of the same. They're close, like an estimate. All right, so use a graphing calculator to find an exponential model that fits the data. All right, so if you type in the points from the table and you graph, okay, using your graphing calculator, then you can find something, change your table. You know, your x's will be from 0 to 6 and your y's will go from 0 to 20,000, and then you will be able to see the graph. So it's going to give you an R of negative 0.99. This is a very strong correlation. It's negative because it's going downhill, okay? A and B is given, so this just goes into your exponential function here. So it says, what is the decay factor? Well, the decay factor is your B, remember, so it's the 0.917, but this says round to the nearest hundredth. So it's going to be 0.92. All right, how does this compare to the ratios found in the table? So 0.92, if you look up here, these kind of hover around 0.9 something. So those are all close. So it's similar. All right, to create a residual plot. Remember, a residual plot is just, you want it to hover around 0. So you can see there's a few above and a few below, but these are kind of hovering around the 0 mark. So that means it is a good fit. Okay? All right, that's all for task 5. If you have any questions, please let me know.